Greetings, calculus students. This is 1.2, Analyzing Graphs of Functions, where we'll be going over a lot of ideas, and many of them you touched on already in the P chapter. First, a vertical line test for functions. Are these functions? Well, if you can get a visual representation of a function, you can use the vertical line test to see if it's a function. And when I start trying to draw vertical lines through it, sure enough, they only seem to cross it once, no matter where we go. So we say yes on this one. On what? Draw a vertical line through it. Oh, crosses twice. No, it's not a function. Now, finding the zeros of a function. The zeros, they're called zeros because it's when the value of the function equals 0. So not when x equals 0, that'd be the y-intercept. It's when the y is equal to 0. So to find the zeros of this, we set f of x. To solve this, I brought this one up because this involves that little trick here where you can see if you've got a cubic, you can see if you got something in common in the first two, and we do x squared. Leaving pi x minus 5. And now the last two we can pull out minus 9, leaving x minus 5 again. So that now x minus 5 is a common binomial factor of both these terms, these two terms. So we can factor that out, and you get x minus 5 times the quantity x squared minus 9. And that factors as well. Each of those factors equals 0. Visually, we can see the zeros as where it crosses the x-axis. So, let's see, there's another one there at 3, and there's the other one at -3. So the zeros are also called the x-intercepts. X-intercepts. That's what we had on the last page, right? Sure enough. Yeah, 3, -3, and 5. Okay, they're also called roots. Now, determine intervals in which a function is increasing or decreasing, and determine relative max and mins. Well, increasing basically is this going up idea. If we're increasing like that, decreasing if we're going down. Formally, it goes like this. If x1, so we can have an interval like this. This is increasing over the entire interval because no matter what I pick for x1 and x2, if x1 is less than x2, then f of x1 is less than f of x2. The y coordinates are less as well. Basically, the idea of increasing that is as you go from left to right, the values are getting bigger. In contrast with decreasing, if x1 is less than x2, as you go from left to right, the function's going down. So let's make a bigger squiggly new function here. That's decreasing the whole time. Because no matter what points, what pair of points we take in the interval, as we go from left to right, the y values, f of x1, are going down. So f of x1 is bigger than f of x2. Relative max is basically, the key word here is relative. Relative to the other points around it, it is the biggest. So this is an example of a relative max. Relative max. Okay? Where we go from increasing to decreasing. And relative min, the other direction. Where we go from decreasing to increasing. It is smaller than anything around it, relative min. And we'll get more into the big ideas of absolute max and mins later. But for right now, that's our relative max and min. So let's look at the same function we had before. Before we focused on the zeros here at -3, 3, and 5. But now we want to locate the relative max and mins. Now where these are exactly, that's kind of hard to tell. Your calculator can find them for you. Let's try and estimate them on the graph here. Right about there. Right about there is a what? The thing about this, we go from increasing to decreasing. So that's a relative max. We keep decreasing after that point until we start increasing again. So down here somewhere, maybe around 4, is a relative min. Okay? Go to review the function. And notice I can drag this around, and notice what's happening on the left there to the values of the function. See how when we're below the y-axis values are negative. At -3 we hit 0, and then the values are positive. At 3 we hit 0 again, and then they go negative. At 5 we hit 0, and then they go positive again. So it's easy to see on a graph when a function's negative, positive, or 0. It's a little trickier to see when it's increasing or decreasing. And what can help us in that is drawing a tangent line. So I make a tangent, select a point, and then select the function. And there's the tangent line to the function at that point. And as we move this point around now, you can see that the tangent line changes. And the key thing is the slope of that tangent line, which is going to be in the y equals mx plus b form, the m, the coefficient on x. So notice here, when we're to the left of this relative min, it's increasing. The tangent line is positive. Right there at the peak, we hit a 0 tangent line, somewhere in there. And now the tangent lines start having a negative slope. And they hit 0 again, and then they start having positive slopes again. Okay, that's a brief introduction to where we're doing with calculus and how we can see when the tangent line has a slope of 0, that's when we have our relative max. It also occurs over here at the relative min. Okay. Make sure you bring your calculator to class as we go over these topics because it is tricky finding the max and min on your 89. You have got to get a graph going. And under the graph menu, when you're doing that, there's something called the math menu. And in there is something called relative max and mins. But you have to set an interval first. So I'm helping guide you through that in class. Next topic is identifying graph of linear functions. Linear functions are the form f of x equals mx plus b. So when you have something like f of x equals 2x plus 3, we've looked at these before when we were graphing lines in the review. That has a y-intercept of 3 and a slope of 2 over 1 and up 2. There's a linear function. Now let's say f is a linear function and we know these two ideas. F of 3 equals 7 and f of 5 equals 11. Find the rule. Well, f of 3 equals 7 is equivalent to saying the point 3 comma 7. Because you're putting 3 into the function, that's the x. 7 comes out, that's the y. And f of 5 equals 11 is 5 comma 11. So from those 2 points we can come up with the slope. 11 minus 7 over 5 minus 3. So that's 4 halves, or 2. And you can come up with the equation, at least in point slope form. Y minus 7 equals 2 times x minus 3. There's one point where I'm not going to let you just get by with point slope form because we want the f of x notation. So it's y minus 7 equals 2x minus 6. So y equals 2x plus 1. And so we have f of x equals 2x plus 1 for a final answer for the functional notation of the line. Now, the greatest integer function is an example of a step function. We've already looked at some piecewise defined functions. Step functions are interesting because they have a lot of discontinuities in them. And let's take a look at this one. The greatest integer function means the biggest integer less than or equal to x. So when you do the greatest integer of 5.2, it's just going to return the 5. The greatest integer of 112.879, even though it's closer to 113, it's going to round it down to 112. The greatest integer of 3 is just 3. Now what are you going to do with the greatest integer of negative 1.2? Nope, not negative 1. It's going to be negative 2, because negative 2 is actually less than negative 1.2. So the result of this is that you're always taking it down to the integer to the left of that number. And so as we can see in the graph here, it forms these stair steps. And one you can't see in here because it's hiding on the line there is this function. I'm going to trace this along here in red. The greatest integer of 0 is 0. And a half would be 0. So we keep getting 0 until suddenly at 1 it jumps up. So put an open circle there to show that at 1 it's jumping up to 1. And now greatest integer of 1.1 is 1. All these stay at 1. And then it jumps up to 2. So on each of these little stair steps, it's closed on the left and open on the right. Same thing over here. We just looked at negative 1.2, and notice negative 1.2 is going to come down here to negative 2. Okay, on the T89 you use this with int. Say y1 equals int of x. You can look that up on your menu, or you just type in int. It's also called a floor function on the GeoGebra. Even not something we looked at before. Just let's talk about the ideas behind it. And the functional notation test is in even functions, f of negative x equals f of x. So if we look on either side, here's x and here's negative x, they're both going to go to the same value. Like we'll see in parabolas and so forth. And the graph is symmetric about the y-axis. The y-axis. With odd functions, f of negative x equals negative f of x. So when we look at x and come up here to f of x, we get a point. But if I look at negative x, it doesn't come up to that same y value, it comes down here to the opposite of that value. So here's negative f of x down here. And so we see that with the cubic functions. And the graph is symmetric about the origin. It's point symmetry about the origin, 0, 0. Now, if f of x equals x cubed minus x, is this even, odd, or neither? Well, first do the functional test. What's f of negative x? That's negative x quantity cubed minus a minus x. So it's negative x cubed plus x. We can factor out a negative, getting x cubed minus x. And so this is the opposite of f of x. So this is odd. Odd. You can see it right away from this point symmetry, that we can rotate this 180 degrees about itself and it'll be back on itself. That's point symmetry with respect to the origin. Finally, if f is even and f of 3 equals 7, find another point on f. Well, it's even, so f of negative 3 should equal f of 3. Let's say if f negative x equals f3, so that's equal to 7. So another point then is negative 3, 7. Essentially, we graphed 3, 7. And now here's negative 3, 7. The mirror image over the y-axis. Okay? Flange.